Shall we start looking for?
Just
Okay. So good evening, everyone, and I sincerely thank Dr. Dittman to join us for the day where he is going to take us towards the understanding of biases and confidence limits for the data which we look for. We all always fancy for a large data, or we always believe that what data we have, it's a very critical data. But how it can be interpreted rightly, looking at the errors, what we get, and what will be the confidence limits. So this is something which we all need to understand, and we have with us Dr. Dritman for that. So not wasting anyone's time, over to you, Aditi, please. Thank you
okay,
so
sir.
much for
Thank you, sir. Thank you for the kind introduction. So, hello, everybody. Today, the lecture that I'm going to take is going to be a little bit offbeat. Basically, it's not going to follow any specific pattern that you may have heard of in the past. It will be very unlike any and every of the lectures on statistics, biostatistics that you may have heard. So, let me just start it off. That way, it will be more fun. And Uh, just a reminder that I'm very happy to take questions whether during the presentation or after the presentation. Okay, you can stop me whenever you want. It's all about you people understanding what exactly you are dealing with. Okay, so the first thing, what is the point of a research study? I'll start from the very beginning. Okay, what is the point of a research study? A study is conducted when you have some anecdotal information about a topic, but you're not very sure of the results that you're getting from that anecdotal information. That anecdotal information can come from case reports, case series, your own clinical experience, some drug that has been tried out by some sketchy company and it has been given to you, or it is just you are of a very cautious nature and you don't want to believe other researchers and you want to conduct a study for yourself. Okay. So so basically, unless you know anything and everything about a topic, you would want to study more, you want to research more until you get to know anything and everything that is important to you. Okay. But the problem with knowledge in general is that you will never know anything and everything about a topic, about any research study, any question, you will never come to know everything about that topic. There will always be some or the other lacunae, whether you know it or not. There will always be some or the other lacunae in the information that you have about a topic. Okay. So what can you do? Because all the time you're not going to have some part of the information. What you can do is that the information that you have, you should be willing to trust that information so that you can act on it. That is the point of a research study. Okay. You try to gather information and then you try to find out whether that information is good enough or not for you to trust it. Okay. And after that, you just assume and presume, hope for the best. Okay. But just remember that you will never know everything about a question. Okay. Now, coming to the topics of errors and biases. Now, these are two terms which are very often conflated. They are actually sort of similar only. So let me just break it down very simply. Okay. Whenever you try to get some information out of a research study, okay, that information may be a little far away from the actual truth. Like suppose this is the actual truth. This is the information that you found from your study. There will always be some gap between the two. Okay, this gap in statistical parlance is termed as error. Okay, now what can this gap look like? It can look like a difference from the actual mean. Suppose your study was to determine the mean of a certain parameter within a population. Okay, there is some true mean that you do not know anything about. So you take a sample, you find the mean of that, and there will be some difference, but you will never be sure what that difference is. Okay, now because it is assumed that the sample mean is not the true mean. Okay, so you are basically a little far away from the true mean. So you are basically committing an error in determination of that true mean. Okay, so that is what error means. Error means when whatever you have found is presumed or is actually different from the reality or truth. Okay, now the errors can be because of two types of reasons. Things that you can correct and you know of and you can correct, or things that you do not know anything about. So the errors can be because of causes that you know. If you know the causes, you can attempt to correct them by making a good study design, by calibrating your instruments, by refining your data collection methods, whatever. Okay. So these type of errors that you know the reason for and you are able to correct are known as systematic errors or biases. Okay. The other type of error is something that you do not know anything about, meaning that error is there, but you do not know the reason for that error. Hence, you will never be able to correct it. Because you don't know the reason, you won't be able to correct it, right? Then why are we thinking about this error? If we are never able to correct it, then why are we thinking about it? Because it helps us in building up the certainty slash uncertainty in the information that you have found. That is why estimation of the other type of error that you do not know anything about, the one that is called random error, you want to have an estimate of that so that you can make some judgment about whether the information that you have found is good enough, precise enough, certain enough or not. Okay. Chalo. So to recapitulate, two types of errors. You know the reason, you don't know the reason. You know the reason, it is a bias, you can correct it. You don't know the reason, you want to estimate it, but you cannot correct it. It's called random error. Okay. Next. Now, the estimate, like I said, you want to estimate the amount of random error that you are making. Okay. So the amount of random error that you are making, the estimate of that is called standard error. I think everybody of you would have heard the term in your biostatistics classes, some point of the time or other. Standard error. Okay. What it means is an estimate of the random error that you are undertaking by calculating something from your sample. Okay. Now the thing is that because we never we never know the true extent of the random error, so you will never have a true estimate of what the standard error will be. So the standard error number is just a number. Okay. The number is calculated based on some presumptions. Okay. What are those presumptions? Two. First, if your sample is too widely dispersed, there is too much variability within your sample itself, then your error is going to be large. Second, if your sample size is too small, then basically you are probably committing an error and the error is likely to be large. So these are the two guiding principles of standard error. Variability, excessive variability inflates standard error, small sample size inflates standard error. So the only thing that you can do to improve your standard error or your estimate of your random error or reduce your random error is to increase your sample size. So imagine like this, if this is your entire population, your sample is this tiny, okay, obviously you will be somewhere far away from the mean. If your population is this much and your sample is this big, then obviously your estimation will be very close to that of the population, right? It is common sense. So because of that, standard error will improve, or it is supposed to improve when you increase your sample size. So random error will reduce. Okay. Now the thing is that this is a conceptual understanding of standard error, one concept of understanding. Okay. How it is going to be used for you is a little different. Okay. So let me go a little deeper into it and try to stay with me. If you are not able to understand anything, stop me. I will reply. Okay. Now, for doing this, what I did was I went to the census of 2021, the Indian census of 2021, and I got the estimate of Karnataka population heights. Okay, so Karnataka has got a huge population, that is 52.8 million. Okay, so a census, what it does is it tries to get an estimate of the entire population. The estimate that they found here, that they calculated here, was the average height of individuals in the age group of 18 to 25, I think, something like that, 18 to 24 or 25. Okay, so within this age group, what was the average height of people? Okay. So they calculated it and they have published that. Okay. Using that published data of mean height, what I did was I simulated the data of the entire population, because mostly your these type of data are going to be a little normally distributed. Normal distribution means that you have got one peak, okay, that is unimodal and symmetrical tails. Okay, so under that assumption, I simulated the data of 52.8 million people, and I made a histogram of that here. Okay, so this is nothing but a histogram of Karnataka population heights based on the census of 2021. Okay, now what I want to show you is that from this population that I simulated, okay, I pulled, I sampled basically people. Okay, I sampled from the simulated data. Okay, and the sample data, I drew histograms of that. If you are able to see this entire this graph, this is basically of a sample size of 10. Okay, so with a sample size of 10, you are able to see how many like there were of the height, I think 162, there was one person, that is count of one. 163, there was one person. 164, there were two people, so on and so forth. Okay, now just observe what happens to this graph, this histogram, as we increase the sample size. The sample size will be increasing right up here. Okay. Yeah. So as you see, the sample size is increasing, and you can see that it is starting to become a sort of a histogram. Can you see? It's starting to become sort of like a bell curve. The sample size increasing to 350, 380. Now it has almost become a bell curve. Okay. Now, as we increase the sample size to 1000, you will see that it will become more and more resembling that of a bell curve, and it will stay like that. Okay. So there I wanted to show you that if you collect enough samples from a population and that sample is sort of symmetrically distributed in the population, sorry, the parameter is sort of symmetrically distributed in the population, you will end up with this type of bell curve. Okay, this is just to show you, just to demonstrate to you that that is how it happens. Okay. Chalo. Next what I did was that I sampled it again, but I took 1 lakh samples. Okay, I think I took uniform samples, that is small sample sizes, I think around 50 or so. And of those 50 samples, I sampled it 1 lakh times. So basically within the context of the population that I had, I took one sample of 50 people, one sample of 50 people, one sample of 50 people, so on and so forth, until I reached 1 lakh. Remember, this is all a simulation. It can all be done very easily if you know a little bit of coding. Okay, it's not very difficult. Okay, so I sampled 1 lakh samples from that population. Okay, now, then after that, what I did for each of those samples, I made a density curve. Density curve is something like a histogram. Think of it like a histogram. Okay, so I made histograms of all of the samples that I pulled out of that population, 1 lakh. Okay, and I colored them according to how big they were. Basically, how much was the area under the curve, something like that. I colored them according to that. So it makes for a very pretty graph, as you can see. So these are all the 1 lakh samples. What the thing that I want you to notice is that each time I sampled, the curve was very different. Although the overall shape was sort of like a unimodal and symmetrical, sort of symmetrical, sometimes the data was, the mode was skewed. That was, it was to one side. Sometimes the central point, the most frequent values were very narrow, meaning that there were very few samples with that very high value. Sometimes it was much more spread out like this one. So you are going to get a lot of variability if you have small sample sizes. This is just to demonstrate that the amount of variability that you can have if you sample from the large population multiple times. Okay, now imagine each of those samples could be the sample that you have taken for your study. Okay, so that is why I say that you will never be certain of the truth. You will be very, mostly, you will be very far removed from the actual truth. All you can do is try to get an estimate of how far away you are from the truth and just pray to God that it's small enough to be trusted by your reviewers and your peers. Okay. Next, now I'll come to the conceptual understanding of the thing. Okay. Now the thing is that here what I did was for each of those 1 lakh samples that I took, the sample of 51 lakh. Okay. For each of those, I calculated the mean of those 1 lakh samples. Okay. Each sample will have one mean, right? And then I drew a histogram of those means. Okay, so means of the samples that I took. Okay, so here the green line, that is 166 centimeter, is the mean height of the entire population. Okay, this is the middle point of the entire population that I had simulated. Okay, each of these bars is from the data that I pulled out, the 50 samples that I took, and these are the means of each of those. Okay, so you can see that even the means that you calculated after sampling the same population 1 lakh times, they also formed a bell curve. It's a very funny thing, no? Now let's take one step further. What was our conceptual understanding of standard error? How far you are away from the true mean. Okay, so here, because we have simulated the data, we have the actual central mean, that is the true population mean of 166 centimeters. And I have the means of all the 1 lakh samples that I took. So it is easy for me to calculate the errors that I'm anchoring within each sample. So basically the difference of your sample mean minus the actual true population mean. So I took the difference of those. Okay. If I take the difference of those and I plot them, they also form a bell curve. So dispersion of sample means from the true mean. This is that thing. Okay. Now the funny thing is that if I calculate the standard error for your any sample that I take, okay, that standard error is going to be diffuse depending on how far away it is. Okay, but the average standard error of all of those I calculated to be 0.671. Okay, now the next thing is that what conceptually the another definition of standard error is the standard deviation of the difference of your mean from the true population mean. The standard deviation of the error that you are incurring. That is another definition of standard error. Okay, so if I calculate the standard error for this, it comes out to be 0.664. That is not very too far away from the 0.671. That is the calculated standard error for that entire population. You understand? So basically what I'm trying to show you is that your standard errors have got multiple definitions and each of them connect to each other if you think deeply about it. One is an estimation of the random error that you are incurring. Second, the standard deviation of the errors that you will commit if you sample the population multiple times with the same methodology. Okay, so dispersion of your errors that you are going to be incurring is standard error. Get the idea? Now, let's go on to the next part of it. That is the things that sometimes confuse people, alpha and beta errors, power and p-value. Okay. Now, for this, I have got a way of teaching it that I want you to pay attention towards. So imagine that there are two realities. Okay, one is the true reality that you don't know anything about. One is your sample's reality that you have found based on your sample. Okay, now both of these realities can have a effect that you are trying to study as a yes or a no. Okay, like suppose difference of two populations. Like suppose you gave two drugs to two groups. You want to see the difference between the two. Okay, suppose in real life, in the real reality, you have a difference yes, or in some other times difference no. Okay, in your population reality, like what your population, sample population that you took, from that, whatever you calculated, you can get an answer of yes, there was a difference, no, there wasn't a difference, right? So both of them can be yes or no. Okay. If the reality says no, but your reality says yes, meaning that your calculation says that yes, there is a difference, but truly there is no difference, then that is called committing an alpha error. That is finding a difference when it is not there, or finding an effect when it is not there. Now the fun part, you have no idea what the real reality is. That is why you're studying. That is why you're doing the research, right? So alpha error is sort of like a hypothetical concept. Okay, it is like a hypothetical concept, but it drives the entirety of your analysis process. Okay, now what this exact alpha error is, I will come to in the next section. But for now, just understand that it is when your study reality says something is yes and your real reality is no, that is committing an alpha error. Okay, next, let us come to if your real reality is yes, and your sample reality says no, that means that you're not finding some effect that is actually there. That is called power of a study. Now, the power of a study, practically, for most practical purposes, depends on your sample size. If your sample size is big, your power will be high. Just leave it at that. Okay. Next, that is for beta error. And beta error opposite is power. And that is basically a probability of finding something when it is there. And the only way to increase that is by increasing sample size. Okay. Next, come to the alpha error. Okay. Now, if you want to avoid alpha error, avoid committing alpha error, then you have to have a boundary point for that alpha error. Okay. How much alpha error you are ready to tolerate? How many percentage of the times, if you did the experiment infinite number of times, how many percent of the times, if the real reality was yes, you are ready to, the real reality was no, you want to say yes. Okay, that is what alpha error is. It's like a hypothetical boundary line. And that is exactly what your p-value is also. Okay, now this alpha error and p-value will start making sense when I go to the next section. Just bear with me for now. Okay. Next, what are confidence limits? Okay, confidence limits are, okay, let me give you not even an example. Let me just tell you that if you sampled from your population, okay, the true population mean is this much. Okay, suppose this much far away. Okay, now the confidence limits tell you that around your sample mean, okay, in a range around the sample mean, the population mean will lie. That's all it tells you. Okay. Basically, the hypothetical estimates or outer limits of the population mean or population estimate around your mean or around the estimate that you have found. Okay. So like suppose if the true mean was 10, your population mean came out to be 5, and the confidence limits calculated were from 15 to minus 20, suppose. Okay, so your population mean it will lie somewhere between 15 and minus 20. That is what the confidence limits tell you. If the confidence limits are too wide around the population mean, around your sample mean, or around your sample estimate, then you are not very precise with your results. You cannot trust your result. If they are narrow, then you can trust your result. That is one of the meanings of confidence limits. Okay. This confidence limits can be calculated based on standard error methodology. It can also be calculated by doing the simulation exercise that I did. Okay, that method is called bootstrapping. And the other method of calculating confidence limits is called analytical, in which you have preformed formulae that you use to calculate the confidence limits. Okay, it basically tells you how dispersed your estimate of population mean is around your sample mean. Okay, that's all that there is to confidence limits. Now I wanted to show you how the confidence limits change as your sample size increases. Okay. Remember, confidence limits are another way of saying standard error, because standard error is used in calculating confidence limits. Okay. So in this graph, this is the graph of all of those samplings, the samplings that I had done. Okay. Now here I sampled in a different way. I kept increasing the sample size from the smallest sample size of 10 to a maximum sample size of 2000. I sampled multiple times. Okay. And in this graph, what you see is the dots that you see, these individual dots, these are the means of each of those samples. And the lines around them, the bars around them, are the confidence limits of your sample mean. Okay. You can see that in the beginning, when your sample size is like close to 250, okay, the confidence limits are very wide. And as you move forward, if you increase your sample size, you can see how your the confidence limits keep getting narrower and narrower and narrower. Okay. So practically speaking, most of the narrowing has happened by 500, but after that also a gradual narrowing will keep happening. So if you keep increasing your sample size, the calculated confidence limits are going to become narrow, because the standard error that you are presumed to be committing at that sample size is smallish. Okay, so remember, it's all a game. It's all calculation of an entity that you have assumed and presumed to be true based on some ideas that you get from nature, basically. If you have a large population, then obviously the error that will be committing will be small, something like that. Okay, so this is what is there about confidence levels. Okay. Now, what I'll be doing is I'll be going over to another presentation in which I'll be telling you the general framework of statistical tests, and that will tie together the ideas of everything that I said previously. Okay. Now, remember, first thing is that the tests that we use for statistical purposes, all of those are based on mathematical methods that have been developed close to 50 years back. Okay. Mathematicians had devised those techniques a long time back. Statisticians adapted those methods for their own purposes, that is the data analysis part. And as researchers, we don't even need to know the derivation of those methods or anything like that. What we need to know is some basic background of the test that we are trying to do, like what are the assumptions that need to be fulfilled before conducting some sort of specific test. And we just need to know how to use it well. That is all you need to know as a researcher. Okay. Next, now comes the meat of the entire presentation. Okay, what is the general framework of statistical tests? Okay, all statistical tests or all research that you do is done to find out some specific effect. That effect can be a difference of means. That effect can be odds ratio or risk ratio. That effect can be a correlation coefficient, a regression coefficient. It can be many different types of effects are well known. Okay, 1 minute. Somebody is putting on chats. Okay. Lenin has asked a question. Is there any outer limits to say that confidence limit could be accepted, or any calculations for that? Okay. So for this, understand that when we calculate the sample mean, okay, the sample mean itself has some boundaries to it. Okay, or when you calculate the effect that you're trying to calculate, they will have some boundaries, meaning that suppose you are trying to find difference between two groups, difference between two means. Okay, the effect that you're trying to see is the difference of the means, right? Now, the difference of the means, if it is equal to 0, okay, then it has no meaning. The more farther away from 0 it is, it has more meaning. Suppose from beforehand, you want to say that this mean is going to be larger than the other mean, always. Suppose. Okay. Now, if that is true, then your difference has to be positive. Okay. So if the boundary limit is 0, then if your population is, sorry, if your mean is uh, positive, okay, but the confidence levels of it straddle that boundary zone of 0, then your then whatever you are trying to find out, the estimate of that is imprecise. Okay. Now understand the conceptual meaning of it. If you have got difference of two means, okay, and you are seeing that consistently this drug is better than this drug in some parameter. So basically the difference has to be positive. Okay. If your confidence, if at the outer zones of your confidence limits, okay, it the difference of means goes towards negative, like it is less than 0. Meaning if, for example, the difference is 8, okay, and your confidence limits are from -2 to plus 15, suppose. Okay, then you are not very precise, meaning that if some of the times when you when you do the same experiment, it can come negative also. That means that you are not very sure of the results, right? That means that you're not very sure of the results, right? But if the confidence limits were beyond 0, both of them, like the mean was 8 and the confidence limits were 2 to 15, then basically you know that 95% of the times, or whatever your confidence levels were, your population mean is going to lie positive. Okay, so that gives you confidence that if the experiment is repeated, then your difference is going to be positive most of the time. Okay, so this is what the boundary line concept of your effect comes into the picture. Let me give you one more example: odds ratio. If that is the effect, you can calculate confidence interval for odds ratio also, right? Now, odds ratio, when there is no effect of the predictor on the outcome, or basically one variable on the other, then the odds ratio is close to 1. Okay. If there is a diminishing effect, meaning that increase of one of the variables leads to decrease in the chances of the other variable, outcome variable, then the odds ratio is going to be less than 1. If increase in your predictor variable leads to an increase in the chances of your outcome variable, the odds ratio is going to be more than 1. Okay. Now, here, because the effect reverses as soon as you cross 1, so your boundary line of odds ratio is 1. Understand? So if your odds ratio comes out to be 2 and your confidence limits are minus 0.5 to plus 5, suppose, then it is not going to be a precise measurement. That means you are never going to get a statistically significant result. That is what it practically means. If your confidence limit are straddling the boundary line, you will not have a significant result. Okay. Another example for ROC curves. Okay. The area under the curve is the line of no return is 0.5. If it is less than 0.5 to more than 0.5, your confidence intervals, it is not a precise measurement. It is not a precise result. You cannot trust the result. Okay. Similarly, correlation coefficient. The boundary line is 0, where your effect reverses. Okay, meaning that if it is more than 1, then your both of the variables are moving together. If it is less than 1, then the variables are moving opposite to each other. So the boundary line is 0 for the effect to be reversing, right? So if your correlation coefficient is 0.5 and your confidence levels are 0.3 to 0.7, then you are in the safe zone, meaning that it has not crossed 0. The confidence levels have not crossed 0. So you are precise enough in your measurement, or you can trust your result. I think that covers the answer. Now let's move on. Okay. So the general framework for statistical tests. Okay, so first you collect the data to observe some effect. I talked about all of the effects, most of the common effects in the previous section. So that is what an effect means. Something that you're trying to measure. Okay. Now, this effect, okay, you are not sure whether it is true or not. So because of that, you try to calculate in some way by methods that have been devised by mathematicians and researchers in the past, statisticians in the past, you calculate an estimate of the error in the estimation of that effect. That is called standard error. Okay. But from that, once you have calculated the effect and the standard error of the effect, okay, what you want to see is your effect big enough compared to the error that you are accruing in that effect. That is what you want to find out. Okay. Now, the easiest way to get that, how big is your effect relative to the error that you are incurring in the effect. Okay. The easiest way to do that is to take a ratio of those. So effect divided by the standard error of the effect. This ratio is a very specific thing called statistic. You must have heard the term statistic. That is a Z statistic, T statistic, F statistic, chi-square statistic, so on and so forth. There are multiple different types of statistics. The broad idea around the statistic is to convert your effect, which can be of any units, and the standard error of the effect, which can also be of any units, to a scaleless number or a unitless number, which can be applied across experiment types. Like if I am measuring difference of SBP or systolic blood pressure between two drugs, and somebody else is measuring a difference of heart rate between two drugs. Okay, so the units of SBP and heart rate are going to be very different. The mean difference that you're finding between the group, the actual number of that is going to be different because of the scale of that number. That is your systolic blood pressure or heart rate, right? One is going to be in a millimeter mercury, one is going to be in beats per minute, right? But if you estimate the effect and you divide it by the standard error that you have calculated from your sample, then you achieve a number which is scaleless, meaning that that same number is applicable in the SBP experiment as well as in the heart rate experiment or any other experiment that you devise. You understand? So this transformation of your effect and your size of your effect relative to your error to a scaleless number. Okay, this is one of the core principles of any hypothesis testing. You calculate the statistic and then you try to see whether your statistic is big enough or not. Okay, now just follow me for a while. Okay, so what you are trying to see is whether the effect is big enough relative to the error that you are accruing. Okay, now imagine for a scenario where the effect is actually zero. There is no difference in SBP between the two groups. Suppose you imagine a scenario when there's no difference. Okay, then the effect is literally zero. So that statistic is also literally zero, right? Now, this scenario, when there is no difference, when the statistic is zero, is called the null hypothesis. Okay, so so basically what you do is you basically assume that there is no difference between the groups. Okay, now the no difference between the groups, the difference will never be exactly zero. It may be exactly zero. Okay, according to the null hypothesis definition also, it may be exactly zero, but many times the effect will be a little large or a little smaller than zero. Okay, but the probability of it to be closer to zero is high, and the probability of it being away from zero, like much larger than zero or much smaller than zero, is less. Okay, so now that comes to what the null hypothesis means. Okay, so this is what a null hypothesis looks like. When your statistic is exactly equal to zero, okay, and the probability of it being close to zero is high, while it being away from zero is low, symmetrically. Okay, so that is what your null hypothesis means, and that is what a distribution is in statistics. You must have heard the term standard normal distribution, T distribution, F distribution, chi-square distribution. Distribution is nothing but a function, a formula, which connects the statistic and the probability of it being equal to or less than that statistic number. Okay, so probability versus the actual statistic magnitude. Okay, so this relationship is built by a formula which eventually, if you calculate many values of your statistic and many values of the probability, eventually ends up as something which is called a distribution. Okay, what you actually end up with in a distribution is something called this. This is called a cumulative distribution function, or CDF. This is the CDF of a normal distribution, in which the probability of it being 0 is exactly 0.5, meaning that probability of it being less than or equal to 0 is exactly 0.5. As you go more and more and more higher, like your Z statistic increases, the probability of it being close to, or equal to or less than that number keeps on increasing. You understand? So basically what you are trying to do is you are trying to make a, sorry, what am I doing? So you are trying to make a connection between the size of your statistic that you have calculated and the probability of its occurrence. Okay. Now, if the probability of the occurrence of the statistic is high, right, then you are much closer to 0. So your statistic belongs to the null distribution or belongs to the null hypothesis. If the statistic is large, then it belongs to the tails of that distribution, meaning that you are far away from the actual null distribution. Are you getting the idea? Now, if you are far away enough, then you can say you do not belong to the null distribution. But how do you know you are far away enough or not? To know how far away is good enough for you to say that you are not belonging to the null distribution, you have to preset a probability that I am okay with this much chance of belonging to the null distribution or not. Now, this is what is alpha error. You are setting limits that if the size of my statistic is such that there is a less than 5% chance of this statistic belonging to the null distribution, that is your that is basically statistically significant, or that is the result that I want to get. So you are setting limits of alpha error. Okay. Now you can have the alpha error a little large or a little small, that is up to you. But mostly it is set at 5%. If you are being very pedantic, then you can set it up to be your your 1% also. Sometimes when we are dealing with things which are actually very less in nature, meaning that you are trying to study something which is very uncommon, then you will be trying to get, you will be aiming at an alpha error of 1%, but you will have to, sorry, 10%. Then you will have to justify that how big, why are you justifying such a high alpha error that you are ready to accept the result, even when there is a 10% chance of the result belonging to the null distribution. Okay, so that is where everything ties in. Have you understood it now? Let me. So basically, let's start over again. So you find some effect that you're trying to find out from your study. You calculate the standard error of that effect. You take the ratio of those to calculate the statistic. Okay. From that statistic, you which distribution does it belong to? That is thing that you need not worry about right now. But statistics have different probability distributions that depends on what distribution you are aiming at or what your error histogram looks like. Let's not bother about that right now. But that statistic is then converted into a probability of occurrence of that statistic using a cumulative distribution function. And that cumulative distribution function tells you what is the probability that your effect belongs to the null distribution or not. Okay, this is the outline of entirety of statistical analysis. I hope I have gotten through to everybody in this. If there is any question, you can ask me. So yeah, this is the lecture for today. I wanted to tie in all the principles of the general framework of statistical tests to alpha error and p-value. I hope I have gotten through to all of you and it makes sense. If it does not make sense, you can ask questions. If not, then shall we call it a day?
Thank you, Dr. Ditman.
Thank
I
you, sir.
don't have words to describe how easily you made the thing simplified for understanding, and we'll use this presentation and your explanations to our YouTube, where we can come back and rejoin your sessions. Thank
Sure,
you
sir.
so very much. Thank
Sure,
you.
sir. Thank you, sir. Bye-bye.